Brain scans don't read your soul. They read patterns.
That is the perfect way to start this. We are looking at biology, not morality.
Welcome back to the deep dive. We have a very specific mission today. Usually when we cover a topic like substance use disorder, we rely on the headlines. We say things like, studies show, or neuroscience tells us.
Right. We treat the study as this kind of black box. It just spits out facts.
Exactly. But we rarely ask, what actually happened inside that box.
How did they show it?
Yeah. So today, we are prying the lid off. We're going to look at the actual machinery the method scientists use. When a researcher says, this brain shows signs of addiction, what are they really looking at?
And that's such a crucial question because it takes this all out of the realm of, like, magic and puts it into measurement. These are just very loud, very expensive tools we use to see biological reality.
But they have limits.
Huge limits. And understanding the tools and their limitations actually makes the findings that much more powerful, I think.
So for this, we've gone through a huge stack of sources, everything from nature protocols on fMRI methods, the DSM-5, some really dense text on what's called the IRISA model.
And we absolutely have to talk about incubation. It's this really counterintuitive idea that explains why quitting often gets harder before it gets easier.
Okay, but before we fire up the giant magnets, we have to do the responsible thing.
We do. Just a quick disclaimer. This deep dive is for educational purposes only. We are just exploring the science from the source material. It is not medical advice.
If you or someone you know is struggling, please seek help from a qualified professional.
Okay, so the machinery.
Section 1, the toolbox. I mean, the biggest challenge seems obvious, right? You can't just open up a living person's skull to see how they react to a picture of a beer.
Yeah, definitely not. So we have to rely on proxies, on indirect signals to figure out what the brain is doing. And in addiction research, you see three main tools.
Let's start with the one that looks the most sci-fi. The cap with all the wires.
Right.
EEG.
Electroencephalography, yes. And you can think of the EEG as the speedster.
Because it's fast.
Incredibly fast. Your brain cells, your neurons, they talk using electricity. So
Yeah.
the EEG has all these electrodes on the scalp that just listen. They pick up those electrical waves.
And its superpower is speed.
Temporal resolution, yeah. It can see changes in milliseconds.
So why is that important? I mean, I think of addiction as this long, chronic issue. Why does a millisecond matter?
The condition is long-term, but the reaction to a trigger is instant.
Oh, okay.
In the research, we're looking for a very specific signal. It's called the P300, or sometimes the LPP.
P300, what is that?
Okay, so imagine you're wearing the cap, you're looking at a screen, I flash a picture of a flower, then a chair, then a bottle of whiskey.
Okay.
If you have an alcohol use disorder, your brain does not treat those images equally. About 300 to 500 milliseconds after that bottle appears, the EEG picks up a massive electrical spike.
Wait, 300 milliseconds? That's faster than you can blink.
Yeah.
That's before you've even had a conscious thought about it.
It's basically a reflex. We call it attentional bias. Your brain sends out this electrical shout that basically says, pay attention to this, before you've even, decided to pay attention.
Wow. So I might feel like I'm just passively looking at pictures, but the machine sees my brain screaming, target acquired.
That's a great way to put it. The EEG tells us when it happens, that lightning-fast moment. But it's not so good at telling us where that shout is coming from.
Right, because the electricity diffuses through the skull. It's fuzzy.
Exactly. So for the where, we need the next tool, the cartographer, the fMRI.
The big donut.
The big, loud donut.
And there's a huge misconception here, right? When you see those pictures of a brain with the glowing orange spots, you're not actually looking at electricity.
No, not at all. That's probably the biggest myth in pop science. fMRI measures something called the BOL-D signal, blood oxygen level dependent.
Go.
It's basically tracking the plumbing, not the electricity.
The plumbing. Explain that.
Think of it like this. If a part of your brain starts working really hard, it needs more fuel. It needs oxygen. So the body rushes oxygenated blood to that exact spot.
And the fMRI magnet can see that rush of blood.
It tracks the blood. So when you see the amygdala light up, it just means blood is rushing there, which implies that it's working hard.
Got it. So its strength is location, spatial resolution. It can see deep inside to structures like the striatum.
Exactly. But, and this is a big but, we have to be humble about it.
This is the chicken or the egg problem that our sources kept bringing up.
It's the biggest limitation, really. Most of these studies are cross-sectional. We take a group of people with a substance use disorder, scan them, and compare them to a control group.
And we might say that their frontal lobes are less active.
Right, and the headline screams, Drugs damage your frontal lobe.
But it could be the other way around.
It could be. Did the drugs cause the change? Or did having a less active frontal lobe to begin with make someone more impulsive and more vulnerable to developing an addiction?
And you can't know for sure unless you scan them 10 years before they ever started using.
Which is almost impossible to do. So we're looking at a snapshot. It's an evolving map, not the perfect territory.
Okay, so we have the speedster, EEG, and the cartographer, fMRI. What's the last one? The chemist.
PET scans, positron emission tomography. This is how we actually look at things like receptors. We use a radioactive tracer that's designed to stick to one specific thing. In this case, dopamine receptors.
And this is where we get those famous, really stark images that Nora Volkow pioneered, the side-by-side brain scans.
Yes, they show what's called downregulation.
Meaning the brain is getting rid of its own receptors?
Exactly. If you keep flooding the system with this massive artificial wave of dopamine from a drug, the brain tries to protect itself. It just starts pulling the dopamine receptors offline. It turns the volume dial way, way down.
Which is the biological reason for anhedonia, for not feeling joy from normal things. You literally don't have the hardware to receive the signal anymore.
The hardware has been changed to cope with the flood.
Okay, so those are the tools. We can measure electricity, blood flow, and receptors. Now let's get to what they show us, the network. Because that old, this is your brain on drugs, frying pan idea, it's just too simple.
It's way too simple. It's not one bad spot. The sources kept pointing to a framework called the IRESA model.
IRESA, impaired response inhibition and salience attribution. That's a lot.
It's a mouthful, but the concept is actually pretty simple. This is our first real clip moment here. Think of your brain as a car with two competing drivers.
Okay, driver number one.
That's the salience network. It's deep in the brain, the ventral striatum, the amygdala. Let's just call it the gas pedal. Its job is to spot important things in the world. Food, danger, mates, and scream, go! That's important. Get that.
It assigns value to things.
Exactly. And driver two?
The brakes.
The brakes, that's your executive control network, your prefrontal cortex right behind your forehead. Its job is to say, hold on, is this a good idea? What are the long-term consequences? Maybe we should stop.
And in a healthy brain, they're in constant communication.
Right, a constant negotiation. But what the IRESA model shows is that in addiction, that line of communication gets severed. The gas pedal becomes hypersensitive. It gets stuck to the floor.
The brakes.
The brakes go offline.
Is that literal? Like, do they actually stop working?
Well, in fMRI studies, when they have people do tasks that require impulse control, like a go-no-go game.
Press the button for green, but don't press it for red.
Exactly. In people with substance use disorder, when that red stop signal appears, the brain regions for braking, they just don't activate as much. They show decreased recruitment.
So it's not that they're choosing to ignore the stop sign. It's that the machinery to even see it and press the brake pedal isn't turning on properly.
That's the physiological reality we're seeing. And here's where it gets really kind of scary. There was this study by Lay and colleagues in our sources. They scanned people with heroin use disorder while showing them drug cues.
Okay.
And they found they could actually predict who was going to relapse up to 3 months later. Based purely on how much their ventral striatum, the gas pedal, lit up during the scan, a hyperactive gas pedal was a massive predictor of future relapse.
So the machine could see the risk before the person was even aware of it.
In a statistical sense, yes. It shows that the wanting system is just overpowering everything else, often below the level of conscious awareness.
Which is a perfect transition. Section 3, cue reactivity. We keep saying the brain reacts to cues. In the lab, what does a cue actually look like?
To a scientist, it's just a Pavlovian trigger.
The belly and the dog.
That's it. So in the lab, they do these studies called FDCR, fMRI, drug cue reactivity. You're in the scanner, and they just show you pictures. A syringe versus a pencil, a glass of wine versus a glass of water.
And I read some studies are even more intense. They pump smells into the scanner.
They do. They have these little tubes that can deliver the scent of alcohol or cigarette smoke right into the MRI. And the sources point out something fascinating about paraphernalia.
It's not just the drug itself that's the cue.
Not at all. A picture of a specific lighter, a rolled-up bill, a dirty ashtray. These things can light up the salience network just as intensely as a picture of the drug. The brain learns the entire ritual.
There was a detail in the Nature Protocol's source about expectancy that really stood out to me.
Oh, this is critical. If you put a smoker in the scanner and show them cigarette images, but you tell them beforehand you absolutely cannot smoke for 4 hours after the scan, their brain has a pretty moderate reaction.
Okay.
But if you tell them you can go for a smoke break immediately after this, their reward centers light up like a Christmas tree.
So the brain's reaction changes based on whether it thinks the reward is actually available.
Exactly. It's already preparing the body. It's starting the engine because it knows it's about to go.
All right, I want to get to the most, frankly, unsettling part of this research.
Yeah.
The invisible cue. This is the backward masking study.
The work from Childress's lab. Yeah. This is our second clip moment because it really makes you question free will.
So explain the experiment.
Okay, so they flash an image of a drug cue, like a crack pipe on a screen, for just 33 milliseconds.
That's, what, a 30th of a second?
It's too fast to consciously perceive. And right after it, they mask it by showing a neutral image, like a flower. So if you ask the person, what did you just see? They'll say, a flower. They have absolutely no conscious memory of seeing the pipe.
But the scanner tells a very different story.
The scanner shows their amygdala and their ventral striatum lighting up. The primitive fast part of the brain saw the cue, recognized its importance, and triggered a craving response before the conscious, thinking part of the brain even knew what happened.
That is, wow, that's terrifying.
But it explains that out-of-the-blue craving, doesn't it? Someone's just walking down the street feeling fine, and then boom, they're hit by this overwhelming urge or anxiety and have no idea why.
They think they're failing or going crazy, but maybe their peripheral vision just caught a flash of something, a color or shape.
And their amygdala recognized it. And because the conscious mind never registered it, there's no explanation. It just feels like this phantom urge that came from nowhere.
And that drives the wanting we talked about, even if the person doesn't like the drug anymore.
That's the core of the tragedy. The wanting system is automated. It's hijacked. It can push you toward a behavior you consciously hate because the machinery is just running faster than your ability to stop it.
Okay, that is incredibly heavy.
Hmm.
But it's also validating for anyone who's felt that struggle. So let's pivot. Let's make this practical. How does someone listening use this information?
You have to become a scientist of your own life. You take the principles out of the lab and into your living room.
So practical takeaway number one, map your own data.
Yes. If your brain is an association machine, you have to figure out what your personal associations are. You have to identify your cues.
And you mean literally write them down, the who, what, where, when.
Literally. Is it a specific street corner? Is it the notification sound on your phone? Is it 5 p.m. on a Friday? Is it a text message from one specific person? These aren't just bad habits. They're hardwired neural pathways.
And the act of writing them down,
Yeah.
what does that do?
It drags the cue from that invisible 33 millisecond amygdala response into the conscious, visible prefrontal cortex. You bring it into the light. You give the brakes a chance to even see what's coming.
Okay, speaking of the breaks, we have to talk about the incubation of craving. This was a finding that just seemed to go against all common sense.
It really does. And this is our third clip moment because it is so important for people in early recovery. The assumption is you quit, day 2 is hard, day 30 is easier, and it's just a straight line down from there.
Right, time heals all wounds.
But the brain scans show the opposite can happen. In the reward networks, cue reactivity, the brain's reaction to a trigger, can actually increase for the first few months of being clean.
Wait, say that again? At 60 days sober, my brain might react more strongly to a trigger than it did on day 6.
Yes, that's incubation. The system becomes sensitized as it's trying to rewire itself. It often peaks somewhere between 1 and 6 months out.
That's crucial information. Because if you're 2 months in and you suddenly get hit by the worst cravings of your life, your first thought is, I'm failing? This isn't working? I'm going backward.
Exactly. And the shame from that thought can be the very thing that leads to relapse. But the science says, no, you're not failing. You're right on schedule. This is a known biological phase.
It will rise, and then it will fall.
It will. Knowing that is everything. It separates the person from the process.
Okay, so map your cues and expect the incubation. What about the broken brakes? If my PFC is weak in that moment, what do I do?
You build a cue firewall.
A firewall.
Look, if we know the internal brakes are unreliable when a cue hits, the blood flow literally isn't getting there, then you can't rely on willpower in that moment. You have to outsource the brakes to your environment.
So you create friction before the cue ever arrives.
Yes. A firewall isn't telling yourself, I promise I won't look at my phone. A firewall is leaving your phone in another room. or deleting the app, or giving your credit cards to a trusted partner.
You're adding a physical step, a delay.
You are buying your prefrontal cortex time to come back online. You are physically engineering your environment to do the job your neurology is currently struggling to do.
It's not about being stronger. It's about being smarter.
It's strategy, not just strength. Don't try to win a neurological battle with good intentions alone. Use physics. Use distance. If you know the gas pedal is stuck, you put a barricade in front of the car.
Man, when you see the data, the P300 spike, the BLD signal,
Yeah.
it just makes it impossible to see this as a simple moral failure.
It is. The science is so clear. This is a chronic medical issue rooted in the circuits of the brain.
It takes the morality out and just shows you the mechanism.
And mechanical problems have mechanical solutions.
To recap, we looked at the toolbox. EEG for speed, fMRI for location.
We saw the IRESA model, the gas pedal stuck down, the brakes offline, and we learned that cues can hit us in 33 milliseconds faster than we can think.
And the practical takeaways. Make the invisible visible by mapping your personal cues. Be patient with the incubation period. It often gets worse before it gets better.
And build firewalls. Outsource your brakes to the environment. Work with your brain's reality, not against it.
If you want to dig into these studies or see those brain images we talked about, the full sources are, as always, in the description.
And if you want a simple template to help you start mapping your own cues, that who, what, where, when idea, just comment CUE and we'll send it your way.
Next time, we are tackling one of the biggest, most misunderstood words in all of science, dopamine.
Oh yeah, everyone thinks it's the pleasure molecule.
But the science says that's completely wrong.
It's not about pleasure at all. It's about something much, much more powerful.
See you in the dopamine episode.